Okay, can you all see the presentation? Okay, thank you. Okay, so let's get started. Okay, so in this week we did two things. All right, the first studio was on the DC motors. All right, so in the DC motor studio, basically we got introduced to the different concepts of the motor, correct, and how to go about dealing with the calculations that are associated with it. All right, so we had this torque sort of equation first that relates the KT, the motor constant, and the current. All right, so basically the current, all right, and the torque are interlinked together. So if the torque remains the same, the current will remain the same. All right, so that is one thing that we saw, and we also saw this other formula, which is the back EMF, where as long as your motor is spinning, all right, and once your motor is spinning, it will start to generate a back EMF, which can affect the amount of current flowing in the flowing into the motor. All right, for the motor constants KT and KE, basically we say that they are both the same, and this is something that we obtained from the data sheet of the motor. All right, and we also saw how to convert RPM to omega using this formula. Okay, in terms of power, there are two power components here. One is the output power, which is the torque of the shaft multiplied by omega. So that is the output power. And then the input power is your what you supply to the motor, which is basically VM and IM together. All right, efficiency we know from earlier studios. Okay, so this is the two main or the main equation, IM and omega. Okay, basically omega is a rearrangement of this. Okay, so if you look at this circuit here, if you draw a loop, we saw that the current is directly proportional to the voltage difference between VM and EB over the rotor's coil resistance. Okay, and since EB is KE omega, all right, we can substitute that into the equation here, and then from there we can solve. Okay, or we have another equation that relates to IM. And by rearranging this equation, I can get the omega formula here. All right, and with this formula, basically we saw two things. For a fixed load, all right, when your load is fixed, it implies two things. Your current is fixed, and so the T shaft is fixed. All right, that is from this formula over here. Okay, so if my current is fixed, all right, if my current is fixed, that means this whole thing here becomes a constant. Okay, my current is fixed. That means if I increase my motor voltage, I will also increase my omega. Okay, so that is the first one. The second one is fixed voltage. Okay, for fixed voltage, okay, let me change the color here. Okay, so for fixed voltage, that means VM is fixed. So when VM is fixed, okay, if my T shaft increases, okay, so if I look back at this formula here, if my T shaft increases, okay, T shaft goes up, that means my current also goes up. Okay, they are both related together. Then what would happen? So if my current goes up here, okay, if this component goes up and my VM is fixed, my omega will start to go down. All right, so these are the two ways in which we can look at this formula, okay, to understand the implications of a fixed load situation or a fixed voltage situation. Okay, so of course we will be exploring this in more detail in the tutorial questions later. Okay, and in yesterday's session, okay, we saw the op-amp. Okay, so I hope I think most of you finished activity 1. Some of you were finishing up activity 2. All right, so if you have not finished it up, please make sure you work on it and just give it a try to make sure it is working. All right, if you are not able to get it to work, all right, no problem. When you come for the next face-to-face session on Tuesday, we can discuss further on whatever issues that you are having. Okay, so we saw that the op-amp equivalent circuit is this. Okay, like I said, this is just a symbolic representation where we look at two things. Firstly, we have two differential inputs, V plus and V minus, and we have an input resistance to the op-amp. And basically what the op-amp does is it provides a gain, which is the based on the difference between the two inputs. Okay, and the output resistance R out is very, very low. All right, so R in is very, very high and R out is very, very low. Okay, and we say that the A is very, very large, approaching infinity. Okay, so these are the few things that we understand based on the concepts of how op-amps behave. All right, so these are some of the parameters that we saw. Okay, and these are the two golden rules, all right, that we need to apply. Okay, in a closed loop system, all right, the output attempts to do whatever is necessary to make the voltage difference between the inputs zero. Okay, so that is why in our analysis we will always take that V plus and V minus are the same. All right, so that is the first golden rule. And the second golden rule is the input draws no current, because we said that the input impedance is very, very large. Okay, close to infinity. So there is no current flowing in to the input terminals of the op-amp. Okay, and we saw these two configuration, the non-inverting. Okay, so basically when you say non-inverting means the input is connected to the positive terminal of the op-amp. Okay, so the derivation yesterday I already showed you, so I'll not go through that again. And for the inverting amplifier, the input is connected to the negative of the op-amp. All right, and these are the two very basic configurations of the operational amplifier. There are of course many different ways of connecting them. Okay, there are many ways. Okay, so later we will look at the studio again, how to connect them in cascading form, that means one after another. Okay, so this is another concept. You may have learned about this maybe in your college or in your poly or some other place, but we want to introduce you to this concept of amplification and gain in the other unit of decibels. Okay, so this, when you're talking about amplification, all right, generally the amplification can become very, very high, very large numbers. Okay, so the representation in decibels, okay, allows us to make the numbers much smaller, so it's a bit easier to relate to them. Okay, but they are both different ways of representing the same thing. Okay, so normally when you talk about gain, okay, so if I take any black box, for example, and I say that this system is providing me with a gain of maybe 100. Okay, so whatever signal that I pass in here, when it comes out, it will be multiplied by 100. Okay, so the gain is described as the V out over V in. Okay, the same thing if I want to represent it in decibel notation. Okay, you just need to do the log operation of it. Okay, and the log operation is basically 20 log to the 10 V out over V in. All right, in this formula here. Okay, so that is basically the power gain. The voltage gain, okay, is still considered as 20 log, okay, to the 10 V out over V in. All right, so I will show you that in a while. All right, how you can calculate the gain, okay, using either the gain formula or the decibel formula. All right, both will give you the same answer, but when you have cascading systems, okay, that means one system after another, then you need to be careful of how you apply the gain in the ratio format and the gain in the decibel format. Okay, so that's the only thing. Okay, so let me stop this and let me switch over. Okay, so for the tutorial questions, I will go through the OneNote that I have. It's easier for me to scribe and explain. Okay, so let's look at the questions. The first question is basically we're having a PMDC motor 12 volt source. Okay, so this is basically your VM, and then you have a no load speed. Okay, so no load speed. All right, that means you have basically it's at the time when it's free running. All right, there is no load attached to the motor, and this is a stall torque. Okay, so when you say stall torque means the motor has stalled. That means it's not moving. All right, so these are some of the parameters given to us, and now we are told that we are going to be running the motor at 2500 rpm, and we are asked to find out all this information. Okay, so how do we go about finding out this information? Okay, so the first thing is we want to convert the rpm into omega. So 3800, okay, we want to convert to rpm, sorry, convert to omega. So to convert to omega, basically, okay, to convert to omega, we know that the formula is written as omega equals to 2 pi times rpm over 60. Okay, so you just plug in that. So this 3800 rpm will translate to 398 radians per second. Okay, so that is the first thing that we want to do. Okay, always convert the rpm to omega. Okay, now the next step, what's the next step? So let's look at the two sets of information we have. So the first one is this, no load speed. Okay, so at no load, okay, so when you say no load, what do you mean? Okay, when you say no load means your torque shaft, okay, is close to zero. Okay, torque shaft is close to zero, and if you relate the formula that says torque shaft is equals to kT multiplied by current, okay, this is zero means this is also going to be zero. Okay, so we are not saying that this is exactly zero. There will be a very small amount of torque, a very small amount of current, but we can approximate it to zero. Okay, so with that understanding, okay, now let's look back at the formula that we have been dealing with. Okay, the general formula which says that Im equals to Vm over Rm minus Ke omega over Rm. So right now I'm telling you that this is zero. Okay, this is zero. So if I rearrange, I basically get Vm over Rm equals to Ke omega over Rm. So I can remove the Rm. So Vm equals to Ke omega. Okay. So what is Vm? Vm is 12 and Ke and omega is 398. Okay, so with this we can get Ke value to be 30 milli. Okay, so the actual unit, if you look at basically what you're doing, we're taking voltage divided by omega. So in terms of unit, it will be millivolt divided by radians per second. So that is the sort of unit for Ke. Okay, because in this case we are relating the voltage Vm over the omega, which is radians per second. Okay, now we also know that Ke is equals to Kt. Okay, which means both of them are 30 millivolt over radians per second. Okay, so that is the first thing that we can find given the information that the no load speed is 3800 rpm. Now let's look at the next piece of information that we have. The next piece of information we have is this, the stall torque. Okay, so what is a stall torque? Okay, so again, stall torque is, so now the next information is at stall. Okay, when I'm stall, my torque is given as 30 millinewton meter here. And what is the formula that we have? We know that the torque is equals to KT multiplied by IM. Okay, so if I relate back to this, we can say that T, which is 30, equals to KT, which is also 30. Okay, so this is also 30 milli, this is also 30 milli multiplied by IM. Okay, which means that IM is equals to 1 ampere. Okay, and the other thing that we also know is at stall, that means your motor is not moving, so omega is equals to 0. Okay, so putting this back into the equation, Im equals to Vm over Rm minus Ke omega over Rm. So now we say that omega is 0 means this whole thing is 0. Okay, so what you have left is Im equals to Vm over Rm. So in this case, the current is 1, the voltage is 12, okay, over Rm. So Rm is equals to 12 ohm. Okay, so given the two information on the stall condition, okay, a stall torque and no load speed, we can actually derive quite a few parameters. We can derive Ke, Kt, okay, like what we saw here. Okay, then from there we can derive your Im, okay, and then your Rm. Okay, so these are all the important parameters that we can derive now. So let's go on to the next part here, which is asking us to find all these important parameters here. So let's look at the first one. So now we are operating at 2500 RPM. Okay, okay, maybe yeah, come this side. Okay, so right now I'm going to operate at 2500 RPM. So at 2500 RPM, what is happening? Okay, so the omega, in this case 2500 RPM means omega, you convert, you get 261.8 radians per second. Okay, so let's look at all the things we need to calculate. The first thing we can calculate is, for example, I. We know that I, again, the formula Vm over Rm minus Ke omega over Rm. Okay, so putting in the numbers, you get 12 over 12 minus 0.03 times 261.8 over 12. You'll get 0.346 ampere here. Okay, so that is the current that you will flow into the motor at 2500 RPM. Now the next thing is the torque. Okay, the torque at 2500 RPM is again Kt multiplied by the current at 2500 RPM, which is so Kt is 30 milli multiplied by this, you'll get 10.4 milli Newton meter. Okay, so that is your torque. Okay, the next thing is your back EMF EB, which is omega multiplied by Ke. So again, Ke is 30 milli okay, so what is omega? So omega is this 261.8 multiplied by 30 milli, you will get 7.85 volt. Okay, the power, okay, is given by Vm multiplied by Im. So it's 12 multiplied by 0.346, you'll get 4.15 watt. Okay, so that is the input power. Then there's power to the shaft. Okay, power to the shaft is basically torque multiplied by omega. So the torque is given by 10.4 milli multiplied by the omega 261.8. Okay, and that would give me a value of 2.72 watt. Okay, and the last thing that you need to calculate here is your power loss. Okay, so the power loss is basically the loss in the resistance. So you take I square times R. So the current is 0.346, so 0.346 square multiplied by Rm, which is 12. So you'll get 1.44 watt. Okay, so basically the first step, okay, so if you look at all the workings that we have done, the first step is deriving the KE, KT, and IM and RM. Okay, because once you derive this KE, KT, RM, and IM, you can put everything back into the formula here for subsequent calculations. Okay, so this formula plus the other formula such as the KTI or the back EMF formula or the power formula. So all of them are again one way or another using all these parameters. So the first step is to get these parameters, okay, from the information that is given to us. Okay, okay, so everything we can calculate step by step. Okay, so that is basically how you approach question 1. Okay, for question 2, okay, so for question 2, basically you are told that you are using the same motto as question 1 and the load condition is not changed. Okay, so if the load condition is not changed, okay, so one thing you must always remember is if you are having the same load, means you're having the same torque. Okay, and the formula that relates is T is equals to KT times I. Okay, so if my torque is the same, my current is also the same. Okay, so the torque, okay, is directly tied to the load. Okay, same as the current. So as long as the load is the same, the torque will be the same. So the current will also be the same. Okay, so the question that is actually an error is supposed to be Q1, not Q3. Okay, so in question 2, I think they copied the question from the last semester question. So there was a mix up in that. All right, so the question 2 is actually referencing question 1 motto. Okay, so for this, let me see. Okay, so everything else remains the same. Okay, but now what you're having is we are having a new desired speed, okay, of 1500 RPM. Okay, so first thing is translate this into your omega, you get 157.1 radians per second. Okay, and then from there we can calculate a few things. So the first thing we can calculate is what is okay, so first thing is, since the torque is the same, the current is the same. So what is the current from the previous question? The current is 0.346. Okay, 0.346 over here. Okay, so we can use the same current. Okay, so over here, the current is 0.346 ampere. Okay, so that's the first thing. Now Omega we have translated, okay, from RPM we translate to omega. Okay, and now how, if you look back at the circuit, okay, so basically the circuit is drawn such that you have your VM, okay, with your resistor and then your motor. Okay, and this is basically your back EMF voltage, and this is your RM, and this is your plus minus. This is your current IM. Okay, so in order for me to know the voltage, okay, you can relate it back to the same way we do the initial loop. Okay, that means we can say that if I were to draw the loop here, okay, the formula is VM is equals to IM multiplied by RM plus EB, correct? Because the voltage source is equal to the voltage drop across the loop. So VM will be IM RM plus EB. Okay, so that is why we are able to get this original equation here, correct? Because we rearrange it to get IM. Okay, so now with this, I know my IM, right? I know RM, so I need to find EB. Okay, so what is EB? So EB we know is KE omega. Okay, so K we know from earlier question, so 30M milli multiplied by the omega 157.1, I will get 4.71 volt. Alright, so putting this back into the expression here, so VM is equals to IM, which is 0.346 multiplied by 12 plus 4.71, you will get 8.86 volt. Okay, so basically what is happening now is you're having the same motor, the same load. All right, so since my desired speed is lesser, it makes sense that the supply voltage, the VM, will also become lesser. Correct, so that I will actually run at a slower speed as earlier. All right, so that is basically what we are seeing now. Now the next thing is I want to have a VM of 8.86 volt. All right, so what is the duty cycle if the DC source is still 12 volt? All right, so what we are saying is I have the system. Okay, so you can think of it as maybe having a plus 12 volt coming into the system, and I am able to generate some PWM. Okay, that will drive the motor. So this will basically be my VM. Okay, and what should be the duty cycle of the PM? What should be the duty cycle of the PWM signal so that the voltage that I get at the output side is 8.86 volt. Okay, so you just need to relate the percentage. All right, so if you think about it in terms of percentage, you can just say that 12 volt translates to 100%. Correct, that means that is fully on. Okay, that is my supply that I have. Now I have 8.86. So it's just a ratio. So it's 8.86 over 12 times 100, and I will get a value of 73.8%. That means I am supposed to have a PWM duty cycle of 73.8. Okay, so from our studio, you roughly know that 73.8 means around 3/4 of the time you're going to be on, and around 1/4 you're going to be off. So roughly around there. Okay, so you'll get a PWM line that averages out, okay, around the 73.8% mark. Okay, so the duty cycle has to be 73.8%. Now the next thing is what should be the on and off time if my PWM frequency is 5 kilohertz. Okay, if my PWM frequency is 5 kilohertz. So if my frequency is 5 kilohertz, okay, so what is the period? So the period is going to be 1 by 5 kilohertz, which is going to be 200 microsecond. Okay, and out of this 200 microsecond, 73.8% of the time I must be on, and the remaining I must be off. Okay, so the T on time will be 73.8% of 200 microsecond, which will be equals to 147.6 microsecond. And the T off time is going to be the remaining 200 minus 147.6, which will be 52.4 microsecond. Okay, so that will be the T on and T off time for this particular duty cycle that you want to have. Okay, electrical power consumed. So what will be the electrical power consumed? So the total power is Vm times Im. So it will be 8.86 multiplied by 0.346, which will give me 3.07 watt. Okay, now how about the power loss? Power loss again is the loss in the resistance of the motor coil. So it is I square R. So you'll take 0.346 square times 12, which is 1.44 watt. Okay, and interestingly, if you look back at what we did earlier, okay, you will see that they both have the same power loss. Okay, basically because your current flow in both cases is the same. Your load is the same means your current flow is the same. Okay, so your power loss is still going to be the same. Okay, so when you are running at a lower RPM, you are actually controlling the voltage. Okay, but since the load is fixed, okay, based on the formula that relate torque and load, your overall current still remain the same. Okay, the back EMF, will it have power loss? Okay, so the back EMF is basically generated while current is flowing. Will there be losses there? Yes, all right, but in our case we simplify the approach to say that whatever losses can be characterized by the loss in the internal motor resistance. Okay, there are of course a lot more losses. Okay, minor losses within the motor and the way it generates the back EMF and everything. All right, but that would be a whole in-depth study of how the motor works. Okay, so to make analysis simple, we just take it that the only loss we're going to be covering or focus on is the loss in the resistance of the motor coil. Okay, we don't care about, I mean, we don't say we don't care, we sort of abstract out the rest for now. Okay, so that is basically question 1 and question 2. So there in question 1 we are trying to again reinforce the application of the various concepts we studied in terms of the torque, the load, the speed, and how the formulas can be used, okay, to solve the question. In question 2 is the same thing as before.
Players of all time.
Okay, in question 2, the main thing is the PWM and how the PWM actually plays a part. Okay, in generating the voltage that we want. Okay, so just now, even in the presentation, I asked a question, okay, and I think the answer was correct, okay, by the student, that you want to, using the microcontroller to generate the PWM is the most efficient way. Of course, you don't necessarily need to use a microcontroller. You can also use some other device, correct? Can you remember what device you can use to generate a square wave with varying duty cycle? If let's say you do not want to use the Arduino. Yeah, it's the 555 timer. Correct. Okay, so we have used this before. So in the 555 timer also is another alternative, okay, to change the PWM, okay, to what we want by either changing the resistance, or the capacitance. Okay, can you use the bit scope to generate a signal? Yes, you can. All right, and that will give you the required voltage. Okay, but again, in reality, as you saw in the lab, you need to have a driver chip still. All right, because depending on the motor you're using, you may or may not use a driver chip. Okay, if you're having those very, very small hobby motors, uh, then you may directly drive it and it will still work. Okay, anything a bit bigger, okay, you will need some driver chip to and have an external power supply so that you have enough current to drive the motor. Okay, so there's a question, why no load speed current is zero? Okay, so when you say no load speed, okay, so when you say no load means basically the motor is free running. Okay, so when the motor is free running, definitely when you first start up the motor, you need current to flow in. Then only the motor will start to spin. Correct? But the whole idea is if there is no load, okay, if there's no load, if I look at the circuit here, if there's no load, what will happen is the motor will spin until this back EMF voltage will continue to rise, because the back EMF voltage is proportional to omega. Correct? So if it's free running, that means there's no load, your speed can be very high. So when your speed is very high, your back EMF is also very high. Okay, so there will come a point of time where your VM and your back EMF is almost the same. Okay, theoretically, you can say that they may rise to a point where your EB is almost the same as VM, and then there is no current flow. Okay, but of course, we know that since there are losses within the motor, okay, the losses in the internal resistance, your EB will always be a bit lesser, so the current will always be there. Okay, but it is always close to zero. We can say it's close to zero when there is no load. Okay, because your back EMF is almost or very, very close to your VM. Okay, so based on that, your current flow is very, very little. Okay, so that is why we approximate it to zero to simplify the analysis. Okay, so when the current is zero, we relate back to say the torque is zero based on this. Okay, so again, the torque is basically what you can think of it as what you need to overcome the initial frictional or resistance within the motor to start spinning. Okay, but once there is no load, all right, we say the torque is zero because the current is zero. Okay, so yes, you need initial torque. Okay, initially there is some torque to overcome because you need to start from somewhere, correct? But what we are saying is when there is no load and the motor is spinning already, then you reach a point where the torque is almost zero because it's just free running. Okay, so that is why we can simplify it to say that at the point when there is no load, okay, the current is zero and the torque is also zero. Okay, you need some little bit of current. You need some current and torque to overcome the initial torque first. All right, but after that, then you can sort of say that it becomes close to zero because your motor reaches a point where it is just running without any load. All right, so that is the sort of simplification that we take into account. All right, to analyze and understand what is going to happen. Okay, so let me go on to question 3 first. Okay, so in question 3, you are given a motor with a fan, okay, with this expression. So we are given that the fan's load torque is given by this expression, and we have all these parameters here. So let's look at what we have. So we can relate back to our formulas that the torque of the shaft is KT multiplied by IM. Alright, so that is one formula. The other formula is IM is equals to VM over RM minus KE omega over RM. Okay. The third formula is KT is also equals to KE. Correct. So these are three formulas. I mean, there are more formulas, but these three formulas we can relate them now. So what we can do is this whole IM can now be substituted in, okay, to relate the torque KT and IM together. So let's look at how we can do this. So I can say that the torque of the shaft is equals to KT. So what is KT? KT is given as 2.42, okay, multiplied by the whole IM expression. And what is the IM expression? Okay, so put in all the numbers. So we have 50 over 0.2 minus 2.42 omega, sorry, 42 omega over 0.2. Okay, and this is the uh, equation for the torque of the shaft. And you can simplify this to 605 minus 29.3 omega. Okay, and you are told that the shaft and the load are tightly coupled together. That means whatever torque that is seen by the shaft is the same torque that is also seen with the load. Okay, because they are already connected together. So the fan's load torque, as you can see, is given by this expression. So you can now say that they are both the same because they are both connected together tightly. So you write it as 605 minus 29.3 omega is equals to 0.05 omega plus 0.001 omega squared. Okay, and then this will become a normal quadratic expression. Okay, so omega square plus 29.350 omega minus 6050. Okay, so you can put that in your calculator and you will get omega is 20.6. Okay, and you get some negative value, so you can ignore the negative. So your omega is 20.6. Okay, which means that it is running at 197 RPM. Okay, so that is the speed at which you are running. Okay, so in this question, we are basically trying to look at it from a different perspective where you are given some other information and then you are relating or solving the equation based on the torque, okay, that is given to us. Okay, so as long as you understand how to put together the different parameters, okay, into the expression, then the rest is quite it's just the maths. Okay, so the torque of the shaft is the same as the torque of the load because in the question it's mentioned that they are both tightly coupled together. So whatever torque that is seen by the shaft is the same torque that is seen by the load. Okay, so effectively you treat it as the same torque together. Yeah, so this normally this is the way we will look at it, correct? Because the torque is the force that you need, correct, in order to turn the motor with the load. All right, so in this you have an expression for the torque of the shaft and you have an expression for the torque of the load, and they're actually both the same. All right, so it's two different expressions, but they are both relating to the same torque. One is you calculate it from the perspective of the shaft, the other is given to us from the perspective of the load. Okay, so that is why when we calculate the torque shaft expression, we can say that this expression and the other expression is the same. Okay, generally in most cases we can say that they are always the same, because the whole idea is the load will be coupled to the shaft of the motor, correct? So unless something else, correct? Okay, for example, if it's a geared operation, okay, in a geared operation the torque might change. Okay, so the torque of the shaft and the torque experienced by the load may have some difference. Okay, but of course here we did not go through the geared operation and how to look at it. But unless we say I'll give you some other information, you can take it that the shaft torque and the load torque will be the same, because they're both connected together. Okay, which is basically like how you are also driving your motor in the studio. Okay, they are both directly connected together. Okay, so that is basically the the questions on the motor control. Okay, so for the M board, okay, of course, when you're doing up your robot and you're going to do the coding and all, we do not need to go into all these details of the motor characteristics, correct? As long as you can control the motor uh, in your code, okay, using the PWM approach. So I hope you all have tried the code that I gave you, okay, that I emailed to you for the bidirectional control. So in it, there were two options, correct? The short one is basically using the analog right function. Okay, the analog right function, if you have done the self-learning studio, you would understand that it is basically giving you a PWM, all right? So the analog right. Okay, so the analog right function in your Arduino Sketch is basically generating a PWM signal, okay, based on the parameter that you pass in. Okay, so the good part of Arduino is there's always a lot of online help and resources with a lot of sample code. So anytime you don't know anything, you just go and Google for it, look at some sample code, and from there you'll figure out, you know, how to try or what to try, and then, you know, see what happens. Okay, so that is analog right function. The only thing about analog right function is it only works on pins which have PWM capability. Okay, if you look on your Arduino board, okay, there are some of those pins with a tilde sign on it. Okay, so only those pins with a tilde sign on it are ones that support this PWM output. Okay, and it happened that the two pins that we were using in the studio had PWM capability, so that's why I can use the analog right function. Okay, if you are trying to use a pin that does not have this analog or PWM functionality, and you want to generate a PWM, then the only option is to do the other code that I showed you, which is to manually do the on and off. Okay, so you manually need to say do a digital write. Okay, so you need to manually do digital write 1 or 0 for how much time on, how much time off, and so on. Okay, so that is of course a more tedious approach and very inefficient approach. Okay, so as much as possible, if you're doing some project on your own or whatever, you should try to allocate a PWM signal for such uh, operations, so your code is a lot more neater and it's a lot easier to handle. Okay, and another thing, maybe it's not so obvious in the code. Okay, the analog write function is a one-time write and it just works. This digital approach is something you have to keep on doing. Okay, that means if I execute this analog write function for one time in my code and then I do other things, doesn't matter, the PWM will still keep on going. All right, whereas if I were to do the digital write option, I have to keep executing this code on, wait, off, wait, on, wait, and so on. Okay, so you are effectively stuck there, just generating this PWM, and you're not able to do anything else. Okay, so the analog write is definitely a lot more elegant, a lot better. Okay, because you need the PWM, you write it, and you can do other things. Okay, so these are some of the things that you will learn along the way. All right, and you will learn what to use at which time. Should I use digital approach or should I use the analog approach? Okay, depending on the outcome I want to achieve. Okay, so let me go on to the last two questions on the PWM. Okay, so the first question here is on this op-amp circuit that is given to us. So in this op-amp circuit, okay, as you can see, you have a configuration here. Is this inverting or non-inverting configuration? Okay, so it is a non-inverting, correct? And the way you look at it is your V in is connected to the positive. Okay, so it's a non-inverting configuration. Okay, so the next step is we want to analyze the behavior. So we apply the golden rules. The golden rules say that the voltages at both the positive V plus and V minus terminals will be the same. So if the voltage at V plus is 2.6, the voltage at V minus is also 2.6. Okay, so that is the first thing. And we can then do the next approach, which is that the current flowing, okay, there is no current flowing into the input of the op-amp. Okay, no current flowing into the input of op-amp. That means whatever current that from this V out flows through this resistor cannot go into this particular negative terminal. It has to go down to ground here. Okay, so if I were to apply your basic Ohm's law, okay, for this current, okay, at this point here, you can say that the current is equals to 2.6 minus 0 over 56k. Okay, to apply Ohm's law over here, so I will get a current of 46.4 microampere. Okay, and if this current is 46.4 microampere, then this current is also 46.4 microampere. Okay, which means that the voltage drop across my 22 kilo ohm resistor is equals to IR. Okay, V is IR, so it is 46.4 micro multiplied by 22k, which will give me 1.02 volts. Okay, so okay, by the way we do our voltage or node analysis, we can say that this point here, V out is going to be 1.02 volts higher than 2.6. Okay, plus 2.6. So it's going to be equals to 3.62. Okay, so that is how you derive the voltage at the output of the op-amp. So in terms of the gain, okay, they ask you to calculate the overall voltage gain. So the gain, okay, is given as V out over V in. So you can say it's 3.62 over 2.6, and that is 1.393. Okay, so that is in terms of ratio. When I want to convert it to decibels, I just say is 20 log to the base 10 of 1.393 is equals to 2.88 decibels. Okay, so that is basically how you derive this expression here.
Oh, Prof. For the current going through the cable to the negative point of the op amp, there's no current going, right? There's no
Sorry,
current
again, current
from the middle point between the two resistance to
yeah,
the op amp itself, the negative point portion of the op amp.
yeah. So no,
No
there's no
current.
current going in.
Oh, so the whole wire has no current flowing through.
No.
All right, understand.
Okay, so that is basically the first op-amp question. So let me go on to the second op-amp question. Okay, so this is basically what we call a cascading circuit. Okay, that means you have multiple op amps connected one after another, okay, to achieve an overall objective. Okay, when you have cascading op amps, you can analyze them with each op amp configuration by itself and then combine the effects together. Okay, so you don't need to look at it as one big circuit at the same time. You can break it up into multiple subsections. Okay, and then you look at the overall effect at the end. Okay, so that is how you analyze circuits with multiple op amps like this. So on the left hand side, okay, you have something very similar to just now, which is a non-inverting op amp. So let's analyze that part first. Okay, so V in is connected to the plus is 3.6 volts. So the same analysis as just now. So is V in is 3.6 volt, V minus is also 3.6 volt. Okay, and as we saw, okay, since no current flow in, the current that is flowing down to ground is the same current coming out, okay, from the V out. Okay, so this current can be calculated as 3.6 minus 0 over 15k, and that would give me 0.24 milliampere. So the same 0.24 milliampere is also flowing here. So with that, I can calculate the voltage drop here. V is equals to IR. So I'll get 0.24 milli multiplied current flow. You can decide how should I put it? You can decide either way, correct? Because like we have seen before, whichever convention you choose, the answer is either going to be plus or minus. All right, and once you get the answer, you will know whether your initial assumption was correct. Okay, to put it simply, if let's say now I draw the current this way. If I draw the current this way, then if I analyze, what will I get? I'll get I is equals to 0 minus 3.6 over 15k, which means I'll get negative 0.24 milliampere. Okay, and that negative means that the current is actually flowing in the opposite direction. Okay, so you could have taken either way, okay, and still your answer is still the same, because if your answer is negative, then you know that it is actually the other way. Okay, so I times R, so this is 10k over here. So this will give me 2.4 volts. So the same thing as just now. So the voltage at this point here, okay, the voltage at this point here, you can say that it is going to be 3.6 plus 2.4, which will give me a value of 6 volts. All right, so the first stage, so you, like I said, you break it up into two stages. So this is the first stage, okay, and this is the second stage. So in the first stage, okay, you have applied the input of 3.6 volt and you get the output of 6 volts. Okay, now let's look at the second stage. Okay, so as far as the second stage is concerned, so imagine that right now I got a 6 volts here. Okay, I have 6 volts coming of the op amp through the resistor. So let's analyze the second stage. The second stage is basically an inverting amplifier because the input is connected to the negative of the op amp. All right, so we apply the same golden rule. So if the V plus is connected to the ground, that means V minus is also connected to ground. Okay, so in terms of current flow, again, you can take it to be one way or the other. So if I were to take it to be this way, okay, I can say that this current, Okay, this current I is 6 minus 0 over 33k, which will give me 0.182 milliampere. Okay, and since no current flow into the terminal of the op-amp, so the same 0.182 milliampere is going to be here. Okay, so the voltage drop. Okay, so the voltage so the V out. Okay, so if I were to look at the same analysis on this side here for this branch, it will be 0 minus V out over 56k will give me 0.182 milliampere. Okay, so by rearranging, you'll get V out is equals to negative 10.2 volts. Okay, so the voltage, okay, at the output here is negative 10.2 volts. Okay, so this is negative 10.2 volts. All right, so now let's look at it from the gain perspective. Okay, so what is the gain? Okay, so what is the gain of the first stage or the gain of the second stage? How do you calculate? Okay, so if you look at it from the first stage perspective, the gain, okay, is given as what? The output is 6 volt here and the input is 3.6. So it is 6 over 3.6. Okay, so that will give me a value of 1.67. If I were to do the log, okay, so it will be 20 log to the base 10 of 1.67. I will get value of 4.45 dB. Okay, for the second stage, what do you get? Okay, for the second stage, the gain is negative 10.2 over the input, which is 6, which will be negative 1.7. Okay, in terms of dB is 20 log to the base 10. Okay, so for doing a log operation, you need to make sure it's positive, so you have to take the absolute value. Okay, so even though the gain is negative 1.7, okay, you have to remember the negative is just a phase shift, 180-degree phase shift. This is just inverted. Okay, but the amplification is still the same ratio, it's still 1.7. Okay, so you just take the absolute value. So it's 20 log 1.7, which will give me a value of 4.61 dB. Okay, now, so I have two different stages over here. Okay, two different stages. How do I relate the overall gain? Okay, how do I relate the overall gain? Okay, so again, the negative is not, it is not attenuation. It's not attenuation. It is still gain. It is still multiplication. You only say that the signal has attenuated if the gain is lesser than 1. Correct? If the final gain is lesser than 1. That means if, for example, okay, for example, if I want to get a smaller signal, okay, okay, so let's say I connect my op amp this way. So V in and V out. So in this case, we can say that, okay, V out over V in is equals to, okay, RF over RI, correct? RF over RI, but it will be negative because it's an inverting configuration. Okay, if RF and RI, okay, let's look at the gain. If RF is, let's say, 10k and this is 1k, then my gain is negative 10. Okay, which means if I put in a signal, okay, that is maybe 1 volt peak to peak, the output will be 10 volt peak to peak, but it will be inverted. Okay, so it will be inverted. It will be this way. All right, but it is still amplified by 10 times. Okay, but if I were to swap the resistor and put 1K here and 10K here, then what happened? It will become negative 0.1. Correct? It will become negative 0. It becomes a value lesser than 1. So if I put 1 volt inside, the output will be inverted, but it will be from plus minus of 100 millivolt. This is what you call attenuation. That means your output is now smaller than your input. Okay. Do we do that? Yes, we do that. Okay. Sometimes we need to attenuate the signal because maybe the incoming signal is too large. Okay, it's too large, so we want to use the op amp to attenuate the signal and get a smaller signal. All right, so we may use the op amp, okay, in both ways. Either you amplify, you get a bigger gain, or you can attenuate and get a smaller signal. All right, so the negative is just the phase only. It's not relating to the gain. The absolute value is the gain. So as long as the absolute value is greater than 1, that means the output is going to be bigger than the input. Okay, so let's look at the combination of the dB first. All right, now when I have two stages, stage 1 and stage 2, and I have two different decibel, the overall gain, okay, the overall gain, if I were to look at it in terms of ratio, okay, for ratio, you multiply. It means you take the first gain here, which is 1.67, multiply by the negative 1.7. Okay, so you take 1.67 multiplied by negative 1.7, you will get negative 2.84. That is the overall gain in terms of ratio. But if I want to get overall gain, okay, in terms of decibels, okay, then I add them together. So it is 4.45 add with 4.661. Okay, I'll get 9.07 dB. Okay, if you were to do 20 log for this, 20 log of absolute negative 2.8, you will still get the same answer here. Okay, so you just have to remember that if I'm going to do a overall gain calculation, the ratio is multiplied, but for the gain you add. Okay, so that is basically how you relate. So the gain is actually was not officially taught to you in the studios. All right, but we will be using it very soon because we will be looking at the filter operation. That means how we can use this for filter operations. All right, and then we can and then we will look at this gain more frequently. Okay, so that basically sums up the tutorial questions that we had to cover. Okay, does any of you have to leave now for any other class? Anybody? Yes, no. Okay, so there's no response. I assume nobody needs to leave at the moment. Okay, so let me just, like I said, I wanted just a bit of time to explain to you the uh, whole idea of the microcontroller. Okay, so we have introduced you to the Arduino Uno. Okay, and for some of you it is new. Some of you are already very seasoned with it because you've used it before in your other hobby projects or in your school projects. Okay, so what exactly is the microcontroller and why is it very useful for us? Okay, before the microcontroller came along, the only way you can implement anything that you have is either through analog circuits or through digital circuits. Okay, so when we talk about analog circuits, we're talking about things that we've been doing so far, and of course other things as well. Okay, resistors, capacitors, and of course other circuits like diodes, transistors, op amps, and all this stuff. Okay, and of course on the digital side, you have your digital logic gates, okay, and connecting them up to implement logical systems. All right. So of course, all of those things have worked. All right. But the biggest advantage of the microcontroller is it becomes it's a complex chip. All right, that allows you to implement a logical process that is actually expressed in software. Okay. So your Arduino Uno. Okay, Arduino Uno is a microcontroller, and a microcontroller is basically a computing device. All right, you can think of it as a scaled down version of your processor that you have in your handphones, your laptops, and so on. All right, those are general processors. A microcontroller is basically a device that is more specific, okay, with much reduced capabilities. Okay, in this context, the Uno, like what you mentioned just now, you need to first be able to understand that what the Uno does, the microcontroller does, it actually executes instructions. Okay, so on your PC, okay, you are writing your code. Okay, you're writing your sketch programming. Okay, after you write your sketch programming, okay, what you do is you compile, okay, and then you download the code. Okay, so you download the code through the USB. Okay, so when you download the code, this code is actually what? This code is actually basically just ones and zeros. Okay, just a hexadecimal string. All right, but this actually represents the instructions that you are telling the Arduino to do for us. Correct. So for example, you're saying, okay, now take this particular pin and put it to a high. Then wait for a certain number of seconds, then put it to low. So you are giving some instructions in the code. All right, but when you compile and download it, those instructions are now translated to the Arduino Uno. Okay, so a microcontroller, in order for it to execute this code, must have a place to store this code. All right, so you definitely need what you call a memory. Okay, so memory has various aspects to it. You have permanent storage, you have temporary storage, and so on. But basically, your code is something that will always be there, correct? Even if I power off and I power on again, the code is still there. Okay, so that part of it is basically what we call the permanent storage. All right, so it goes into the permanent storage of your system. Okay, the next part is, okay, when I fetch these instructions from memory, I need to execute them. Okay, so the executing part of it is generally handled, okay, by the core of the microcontroller, and that core is basically what we call the CPU. Okay, so in a sense, the CPU has a few parts to it. I don't want to go into all of that, but basically what the CPU or controller does is it fetches instructions, okay, from the memory. Okay, and each instruction is telling the processor to do something. Okay, turn on this GPIO, okay, or fetch this data, or add this number to that number. So it is some instruction you are fetching. Okay, you fetch, you decode the instruction and execute. Okay, so if you look up any material, they will usually uh, express it as 3 different main operations. Okay, we call it the fetch, decode, and execute cycle. Okay, so these are 3 main things that any processor will do for us. Okay, and of course, while it is doing this, some of these instructions could be basic arithmetic instructions: add this with that, minus this, multiply, and so on. And then that result, you may write back to memory. Okay, so that is one thing you can do. Another thing you can do is, like in a case where, like in our studio we saw, you can write some values to pins, the input output pins. Okay, so these are what we call the peripherals. Okay, so a microcontroller also has peripheral blocks. Okay, a lot of different peripheral blocks. Okay, and one of it is what we saw or used so far, is called the GPIO, general purpose input output. Okay, so I can also tell the processor, I can write an instruction to say, okay, this particular pin I want to set to a high, I want to set to a low, or something like that. Okay, and of course another thing that we also saw was the PWM. Okay, so I can also configure this, write a piece of code like the analog write function, and that function will actually configure the PWM block to give me that particular signal that I want. Okay, so inside a microcontroller, you can have a lot of these peripheral blocks, okay, to do a lot of different things for us. Okay, input, output, PWM, maybe analog to digital conversion, digital to analog conversion. Okay, do some timing, do some counting. Okay, so there are a lot of different peripheral subsystems that microcontrollers have, and you must be able to write the software that controls the hardware. Okay, so it all comes back to, okay, when it comes to a microcontroller, you need to look at it as a whole system perspective. That means you need to first make sure your software is written correctly. At the same time, you also need to make sure your hardware is also wired up correctly. Okay, so when I write a code to, let's say, activate the PWM. Okay, so when you run the code and it doesn't work, you need to look at both sides. Firstly, is my software written correctly? If your software is written correctly, the next step is my hardware connected up correctly? Okay, so it becomes your responsibility to look at both ends of it. Okay, so you must also make sure the software is correct, and you must also make sure that the hardware is correct. Then only the whole system is going to work. Okay, so it's not just I build hardware and I test hardware, or I build software and the software should run. Okay, it's now software that controls hardware. Okay, so that is sort of the high level view of the Arduino Uno and how it works. Okay, of course there are more things that I want to share with you, but I think we will start off with this first. All right, the next time that we have some time, I will go into the Arduino actual controller schematic, okay, and how it is interconnected and how these various things sort of come together. All right, so we will start off with this basic understanding first, okay, that your Arduino Uno is a controller, microcontroller, which is, you can think of it as a computing platform. All right, and in order for you to make full use of this computing platform, you need to be able to write the software that will then run on your hardware and control various subsystems. Okay, so the pinouts that you see on your board are those are the different ways in which you can connect to subsystems. So I want to connect a switch, I want to connect an LED, I want to connect a buzzer, I want to connect a sensor. All right, so anything that I want to connect, I can connect to these pins. Okay, but it's not free for all. It's not like I can just choose any pin I like. So some pins are used for specific purposes. Okay, so like what I mentioned just now, if I want to use PWM, I must look out for those pins that have the tilde sign on it. Okay, okay. How about analog to digital conversion? So if let's say I have a signal, an analog signal coming in, okay, and I want to digitize it. Okay, so I need to pass it into my A to D converter. Okay, analog to digital conversion. We will be doing this very soon. And if I want to do that, I can only use specific pins on my Arduino Uno that is written as analog pin. So if you look at your board, your Arduino Uno board, you will see that there are some pins dedicated to say analog. So only those pins can be used for analog to digital conversion. Okay, if I want to do something like that. So there are some restrictions on which pins you can use for some of these specific purposes. All right, so again, this involves some planning, okay, ahead when you are building your project. Okay, so in the next few studios, we will play more with the Arduino, okay, and get to uh, understand a bit more of these peripheral subsystems. Okay, but at the same time, for the project, okay, you are given the M board. Okay, the M board, if you look at your controller, it is not the same as your Arduino, but it's actually still Arduino. Okay, it is the same Arduino platform, but they have sort of rewired it, okay, in a way to suit their hardware design. Okay, so some of the things are already pre-configured. Okay, so the motor control, the RGB LED, and the light sensor and so on. So some of these components are already hardwired onto the board, and they're already sort of preset to connect to certain pins. Okay, so it's good and bad. It's good because everything is already there. Okay, so you can't play around with those configuration, but you have some free pins, okay, to play around and do other connections. Okay, so the M board, okay, when you do the project, there'll be more of software side because you need to understand how the software is going to be written to control the robot. The hardware wise, again, you need to build some components, you need to build some filters, you need to build some light sensors and so on. okay, and then you need to connect them to the MBOT pinout. Okay, so so the MBOT doesn't look like Arduino. It is still based on the Arduino. So it's the same sketch programming language, all right, that you're going to use. The good part is, like I said, since some of it is already pre-built, they have readily available software libraries that you can use to control all these subsystems. So if I want to control the motor, I want to control the RGB LED and so on, you don't need to write the code from scratch. They already have library functions that you can easily tap onto. Okay, so that is the good part of the MBOT. Okay, so for the project wise, okay, the details I think will be released soon. Okay, but you can expect a fair amount of software and hardware as well. Okay, and the hardware will involve some of these things that we are doing in the past. We'll be doing such as ultrasonic sensor, uh, filter, RGB, LED, and maybe light sensor. Okay, so these are some of the options of things that might be coming out. Okay, for the mini project. Okay, so we will come to that. Okay, over the next few weeks. Okay, so thank you. Okay, for those of you who stayed back and listened to this. Like I said, I will share more information. Okay, progressively. I don't want to overload you too much. Okay, so on Tuesday it will be a face-to-face lesson. Okay, and it will be the whole class. Okay, so I will see all of you in the lab. Okay, on Tuesday. All right. So thank you very much. Okay, and I will see you on Tuesday.